have the pleasure to welcome Andrei. He's a PhD student at Mila. I met him, actually I met him at Mila first. He came to our talk in the NLP reading group, and then we met again at ACL. I saw his talk, really great work. So I invited him to come here and showcase his work to all MSR. Thanks, Andrei. All right, the floor is yours.
Yeah, thank you. So yeah, the work is called...
Sorry, one question. Do you prefer to have questions during the talk or after the talk?
Let's do during. If I feel like I'm running out of time, I'll let you guys know and we can adjust.
Sorry.
All right, so the talk is about the training dynamics underlying language model scaling laws, and we identify two phenomena, loss deceleration and zero-sum learning. So what is loss deceleration? It's this abrupt slowdown we see in language modeling loss that happens around 5,000 steps across model sizes. And the key feature is this idea of piecewise linearity in log-log space. This is interesting because it suggests a qualitative transition in training dynamics at the point marked in blue here. We also have other evidence that there's a qualitative transition in training dynamics. We can see both in our work and in other works. One of those is loss landscapes. So here what we're doing is we're plotting loss landscapes throughout training with the training steps coming out of the page towards you. And each slice of this 3D surface plot is basically a loss landscape cross-section along the update direction and the positive and negative direction. And so what we see is that at the point of loss deceleration, we again seem to have a qualitative transition in training dynamics where the loss landscape goes from being very highly curved, very sharp, to much flatter. Another place we think that we see evidence of a transition and something that I find really interesting and hope to wrap back to at the end of the talk is this idea of the emergence of circuits and generalization. So most of the results I'm going to show here come from this paper that was out of Luther AI, where they took a bunch of Pythia models from different sizes, and they showed that circuits emerge consistently at the same point in training across model sizes. What's really interesting is at this point where circuits emerge, here on the y-axis, these are different measures that are meant to capture the emergence of circuits. Each plot is a different circuit. And what we see is the emergence of circuit seems, again, to correlate with the point of loss acceleration, highlighted here in yellow again. These are 4 different circuits. We see the same thing for another set of 4 different circuits. And in the paper, they also look at downstream accuracy. And we see evidence that there's generalization that happens after deceleration more than before deceleration. One interesting exception to this is PSI-QA. And this might sort of make sense if we think that generalization is happening after deceleration and more memorization is happening before, because something like PSI-QA, I imagine, is much more like memorization, benefits much more from memorization than these other tasks. All right, so I hope I've convinced you that loss acceleration, like in and of itself, is scientifically interesting to study, just out of pure scientific curiosity, something we don't understand that's related to a lot of interesting phenomena. But I also want to convince you that loss acceleration might be practically relevant and useful to understand as a foundation to improve language models. So I wasn't sure about these slides, but I ran out of time, so I decided to go with it. But I'm just going to beat on Chinchilla for the next couple of slides. I think it's a great paper, but I think it's useful to make the point I want to make to set the stage for the problem we're trying to solve. So if generalization happens after deceleration, one interesting corollary of that is it turns out that Chinchilla optimal, this notion of the Pareto optimal, compute optimal frontier, roughly corresponds to the point of loss deceleration. And this makes sense because after deceleration, you start getting diminishing returns per flop. So it makes sense that to push that frontier, you would rather have a larger model than more tokens. Again, if after deceleration is where we get generalization, what that would mean is that maybe Chinchilla is suboptimal. I think this is sort of symptomatic of a broader issue, which is that scaling laws have predictive power. They're very accurate at predicting extrapolation, but they have very limited explanatory power. And this is something that physicists have argued for a while, and there's a lot of cool papers out there that make the same point. So let me walk you through the actual Chinchilla scaling law functional form, which is roughly the same as the Kaplan scaling form that was originally published. So here on the y-axis, we have the loss. On the x-axis, we have the data set size, or the number of tokens through our training, assuming single leaf log training. And then the color scale represents the model size. And each line is basically a different model. And then the sort of artifacts you see, like the horizontal dash lines and stuff like that, I'll get into what those mean later. So when I say they have predictive power but limited explanatory power, it's not that they have no explanatory power. There's actually some sort of interpretation of these parameters in the equation on the left. Now I want to walk you through them both in terms of what they say in the paper, the Chinchilla paper, and in terms of like what these actually mean. So the first parameter is basically irreducible loss. No matter how large your model gets, you're never going to get better than that loss. The second parameter, what they say is it captures the fact that a perfectly trained transformer with n parameters underperforms the ideal generative process. What this means is that each curve you see on the plot here, the different yellow to red curves, they each have this horizontal asymptotic, which is basically this term here. It's only a function of n, the number of parameters. It does not depend on d, the number of tokens. And so basically what this is, it's the asymptotic limits of model sizes. The models will never get better than this. And then the last term, which is where I start beating on Chinchilla a bit more, is what they say, it's a term that captures the fact that the transformer is not trained to convert divergence, as we only make a finite number of optimization steps on a sample of the data set distribution. This is kind of very empty. It's a very surface level statement. And realistically, what I think is going on here is that this is just a way of fitting the data better, but it doesn't actually map onto any explanation of how loss evolves with number of tokens. This is I'm making this very provocative, just as a way to highlight the problem I think there is. And the problem is that there's nothing we can do in this model of scaling laws besides scale model size to improve loss. Like really what I think we should look at instead is how figure out how to incorporate this notion of training dynamics and not just asymptotic limits. Because if we understand how models improve performance in terms of training dynamics, well, here I'm going to talk about it here. So the goal of this paper is to understand the training dynamics underlying scaling laws. Because if we can understand or answer this question, then we could potentially improve language models independent of scaling by directly targeting the training dynamics that are underlying how scaling improves loss. I'm going to make a claim in answer to this question. And the way I think language models improve loss is the way I think scaling improves language models is by mitigating loss deceleration. So let me break that down to two specific things. The first one is that they lower the loss of deceleration. And so we see this going from small models in blue down to 14 million, all the way up to larger 7 billion models, that the loss of deceleration consistently goes down. And the second thing is that there's a larger slope after deceleration. So after deceleration, the rate of loss improvement is higher for larger models. To me, this is basically, we can frame this in terms of mitigating loss deceleration, which to me seems very likely to be a phenomenon related to training dynamics, especially if we assume that there is a transition going on at this piecewise linear break that we observe. So this is a very pretty sort of qualitative picture, but how do we actually make loss deceleration? How do we measure loss deceleration to make this observation more precise? The key idea is this notion of parametric measurement. So what we do is we fit smoothly broken power laws to the language modeling loss curves. The equation here is the functional form of the power law. It doesn't matter that much, I think, to understand what's going on. The key idea is that this form parametrically describes the log-log piecewise linearity that we care about. So it really sort of captures these two linear segments that form the underlying shape we see. And so by fitting this power law, we can measure loss deceleration from the resulting fit parameters that capture these two linear segments. There's three measurements we capture. The first one is TD, which is the step at which deceleration occurs, and is the step where the two linear segments intersect. We have LD, which is the same thing but for loss. So again, the loss of deceleration and where the two segments intersect. And lastly, we have RD, which is the log-log rate of loss improvement after deceleration for the slope we observe on the last linear segment. What's really cool is that with these three measurements, we can very accurately predict the final loss. And so what this means is that we can express scaling improvements almost fully as a function of mitigating deceleration as captured by these measurements. So we're no longer just talking about qualitatively relating loss deceleration mitigation to scaling improvements, but we're saying that we can actually account for all scaling improvements with these measurements and how they're mitigated when you scale up model size. I have a little asterisk on fully because, of course, this is an approximation. It's not perfect, but I do think it's a step in the right direction to try to understand scaling improvements from the perspective of training dynamics, but then specifically mitigating loss deceleration. So given the sort of reasoning chain that we want to understand the underlying training dynamics so that we can improve them directly, a natural question is, can we mitigate loss deceleration directly without scaling? And so already we know the answer is yes with different optimizers. In the paper, we do some ablations on different optimizers, notably mu1 and ademimix, compared to a baseline of atom W. And we find that they basically improve loss in very different ways that are intuitively grounded in loss deceleration mitigation. So here we have mu1 in purple. And in terms of how muon improves loss, we can see that the main mechanism is this lowering of TD, the step of deceleration. So basically, it accelerates the point at which deceleration occurs. We can also measure this with our method, and we see that for the different other optimizers like Adam W and Endemamix, we have TD of roughly 5,000, and muon has one of 1,500, whereas the other parameters are much more similar across optimizers. So this is really the way in which muon improves loss by mitigating deceleration. Yeah.
The hyperparameter here, like for the optimizer, like you do like a sweep and check that.
So I did do a small sweep, but mainly we're using the implementation of Jordan Keller on NanoGPT because we're using NanoGPT for these experiments.
Yeah.
It is suboptimal. So like you see here, there's like spikes happening at the end.
Mm-hmm.
This is because Jordan Keller, what he did, of course, he trained to the point of compute optimality and didn't train past that. And so muon was not properly tuned for like overtraining. I know a lot of people have come up with tweaks through like QK logic clipping that makes this more stable. But this observation, I have some slides in the appendix if people are interested. We see the same thing in other published results that have like done much more rigorous calculations. So it's the same thing. muon improves TD, but does not really improve RD. And it also maybe improves LD. It's not that good. Sorry, does that answer your question?
Yeah, yes.
Cool. In contrast, Endemamix, shown here in orange, we can see that it mainly improves loss by improving RD, the slope after deceleration. And again, we see this in the numbers, where Endemamix, is comparable for LD and TD, but has a notable improvement on RD. And this improvement is basically the main reason we see this better final loss for Endemamix. I want to make a small tangent here on muon and other second-order optimizers and why I think deceleration is already useful to try to understand how these optimizers work. Remember this plot of the loss landscapes I showed in the beginning? We see that you have very high curvature at the start of training, then things become flat. So from this perspective, it makes sense why muon or like second order optimizers that are curvature aware would help before deceleration, but not after deceleration. So already we have this kind of insight that I think, people might not really know that we can extract just from the simple abstraction of loss deceleration as a qualitative phase transition. So, like a very obvious thing we could try is just to figure out what makes Endemamix good after deceleration and what makes muon good before deceleration and try to combine the two. Okay. So I hope I've convinced you that loss acceleration is also like useful to understand and that we want to understand it so that we can improve models independent of scaling. And so when I say understand loss acceleration, what I'm really saying is we want to understand the mechanisms that underlie it. So why is there an apparent transition going on? What is this transition, if there is one? I'm going to stop here and do some key takeaways for this section. So the first thing is loss acceleration is a potential transition that we don't understand. It co-occurs with interesting things like circuit emergence and generalization. We can measure it to quantifiably explain how scaling improves language models, specifically in terms of training dynamics. And if we better understood deceleration, then we could potentially mitigate it directly to improve language models independent of scaling. Okay, so the next step is understanding what is the mechanism underlying. Yeah, I see Jean-Michel has a question.
Yeah, maybe just a quick question. So I assume here you're training on just like the regular pre-training task, right? It's not like it's a cross entropy loss on the next token prediction. Is that right?
Yeah.
Okay. And do you think that those conclusions that we've had so far, do you think that they would hold for other types of losses?
I can't make a general statement on this. Do you have any specific losses in mind?
Or maybe just like I don't know, like if you fine tune on specific tasks, which is not, or for example, at that 5,000 step that you are referring to, like would it change if you fine tune on another task, for example?
I think so. I also think an important, like the settings in which you see loss acceleration as discussed in the paper, I think the important aspect is really this infinite data set, infinite data regime, where you're never able to overfit the data, so you never see the same data twice. In terms of loss, I do think this is, specific to cross entropy for now, but I don't see why I wouldn't generalize to other losses like RL type fine-tuning stuff. I can discuss this a bit more. I think like looking at in the next sections when we talk about the mechanisms underlying loss acceleration, we can think about this in a more principled way. Basically, like what we show is loss acceleration as a result of Breeden opposition. So whatever loss reasonably seems to result in Breeden opposition, I think would have a similar behavior, but this is just me speculating.
Just
okay.
Jean-Michel, like for example, Keller, they have the speed running on Cypher. So you see the same deceleration on Cypher. So you see the same?
Yeah, I think you ran experiments. Okay.
It's also important to understand that here learning rate schedule is a bit of standard.
The-
We
the-
don't do it's warm-up stable decay without decay.
Yeah, so we do observe.
So like when you train model, practically you will have a decay at the end, and you will have most likely one more part.
Yeah, there is an S. Yeah.
Yeah.
So,
It does. So we were able to like fit the same type of shape to experiments with cosine learning rate decay if the learning rate decay is amortized over a reasonable number of steps. But if you do WSD, like warm-up stable decay, and you decay very rapidly, then of course you're going to get another like piece-wide discontinuity.
of course.
I do want to be clear that like this loss deceleration, like we can use it to model learning rate decay as well, but I don't think we should. I think learning rate decay is like a separate phenomenon that we should model differently. And there are interesting ways in which the two are related, but I'm not going to get into that now. Yeah, I think this question of like whether we see this in other settings like CFAR or like ResNets for like ImageNet is interesting. It's not something that I want to get into. I already have so much stuff on my plate and I'm not a computer vision guy. But have you seen this kind of stuff in computer vision training? It's sort of like hockey stick shape?
Yeah, I mean, yeah, I wouldn't be surprised to see the same thing in computer vision.
Because I know like when I was writing this paper, trying to find if other people have identified the same phenomenon, you have a lot of papers on saturation or plateaus. But this is different because the loss is still improving even after this transition.
Difference because the distribution shape is different, like it's heavy tail with the language, and the version might be different.
I'm not sure about the FFL. It can be about the infinite data versus like even ImageNet, like you have a finite data, you do several epochs, so like you do converge, and here you kind of don't converge.
Yeah. Okay, I'm going to move on unless there's other questions. Okay, so the next question is, what is the mechanism underlying loss acceleration? Basically, why do loss improvements slow down? I want to stop here and actually be very explicit about what I mean by a mechanism, because a lot of people throw that word around without really sort of saying what they mean. So this is a definition from Glennon and Ilari 2017, the Routledge Handbook of Mechanisms and Mechanical Philosophy. And this is basically a bunch of philosophers of science arguing about what a mechanism is, and they can't agree on anything. The thing they do agree on is a sort of minimal definition that is perhaps not very precise, but at least captures the main idea. And so a mechanism for a given phenomenon consists of entities or parts whose activities and interactions are organized so as to be responsible for the phenomenon. So this idea of we want to target training dynamics directly to improve language models independent of scale, like really, you can think of this as, you know, like a medicine targeting a mechanism to cure a disease. We want to identify the parts in the mechanism and we want to target those directly so we can get the same phenomenon without necessarily scaling. In terms of loss acceleration, one way we can have a mechanistic pairing of this is in terms of per example interactions. So in this case, the phenomenon loss acceleration we care about is this notion of the overall change in loss, delta big L approaching zero. And the interaction, the entities, the parts in the mechanisms, those are the per example loss improvements. And we have this nice functional relationship between the two things. So in this framing of per example interactions, there's really two potential mechanisms for loss acceleration. The first one is that loss acceleration occurs across tokens. So basically per token changes in loss, shrink in magnitude on average. And so we see this here in the top box labeled 1, where before deceleration, you have pretty large loss improvements. And then after deceleration, they kind of all shrink to a much smaller magnitude. The alternative mechanism, the one that we're proposing, is zero-sum learning. So in zero-sum learning, what happens is that per token changes in loss increasingly cancel out. So they don't necessarily get small in magnitude, but you get more positive and negative. They cancel out in larger and larger portions, bottlenecking the average and the overall loss improvement once you pull those together. I'm actually curious at this point to get people's opinions before like having heard of this paper. What would people have thought is going on? Because most of the people I talk to think that number 1 is what was going on. I'm curious if this is like an accurate, if this is representative. So I guess just in the room, like show of hands, who would have thought number 1 is what's going on?
Yes.
And would anyone have thought number 2 is going on? And if so, like what paper did you read? And please tell me, because I can't find anything on this. Okay, so no one has number 2 except for Kate. All right. So this is good. I have more data points now.
Yeah. So there is a rich literature that shows that basically when you train, like for example, there are some forgotten examples and stuff. So that might also, I mean, number one, if I understand correctly, it's just saying that the loss on every token decreases always. Seems hard that it occurs on practice. But I would be surprised if loss of one token consistently increases while training goes. I don't know if I'm making sense.
You're saying like you wouldn't expect like some tokens to just get worse and worse and worse.
Exactly.
Yeah. Yeah.
Okay. So
It's not about like they're not consistently increasing.
Yeah.
Okay. So one step I would say too. Yeah.
Okay. All right. So we have these two potential mechanisms. A lot of this paper that is really about going from this hypothesis to something we can verify more rigorously. And so the question we have is, how do we validate a mechanism M as a how do we validate a mechanism M as being responsible for a phenomenon P when you have potentially other contributing factors C? And so we break this down to 3 steps. The first one is to measure M and P. And so the first thing we want to do is by measuring M and P, we can confirm that the two things co-occur. If they don't co-occur, then we kind of already rule out the hypothesis. But this is not enough to establish a causal relationship. To do that, the next thing we do is we derive the phenomenon or the measurement of the phenomenon as a function of the mechanism and the other contributing factors or the measurements. And this derivation, this relating the mechanisms to the phenomenon in a quantifiable way, allows us to disentangle the effects of the mechanism from the contributing factors on the phenomenon. And the last step is once we have the derivation and the measurements, we can basically plug everything in and quantify the relative effect of the mechanism on the phenomenon versus the other factors. This is all very abstract, but it's a pattern that we use over and over again in the paper. So I didn't want to sort of present it to you as is. So now let's actually go through these steps to show how zero-sum learning is the mechanism that is underlying loss deceleration. So first we measure zero-sum learning as this destructive interference in, for example, change in loss. This is the equation. I'm going to walk you through the variables in the equation. I think it's really intuitive. So the first term here, delta big L star, you can think of it as this idealized sum where there is no destructive interference. So whereas basically it's the average or the sum of the absolute values of the changes in loss, because this gives you the expected sum in the case that there is no destructive interference. In contrast here, delta L, big L, is the actual sum with destructive interference, and we slap an absolute value on that. And so then we end up with a numerator in the equation, which you can think of as the amount lost due to destructive interference. And then we divide that by the sort of upper bound of delta L star, such that, this measure D of delta L, destructive interference, will approach 1 if you have complete zero-sum learning, and will approach 0 when you have no zero-sum learning. So this is something that we made up for the paper, but I think it's pretty intuitive and clear. Does anybody have any questions about this measurement? Okay, I'm going to move on then. So we measure zero-sum learning through this destructive interference measure, and we see that zero-sum learning does occur with loss acceleration in the sense that D rises up towards 1 at deceleration. And again, D approaching 1 corresponds to complete zero-sum learning where things interfere almost completely. And we can also see zooming in after deceleration that scaling up model sizes mitigates zero-sum learning in the sense that you have lower D consistently throughout training after deceleration. So we've established the sort of co-occurrence, but we haven't established the causation. The way we do that next is by deriving the effect of ZSL on deceleration. And so to measure the phenomenon, the loss acceleration, we look at delta big L at the absolute value. And when you get deceleration, what happens is delta big L approaches 0. And so we want to understand out of the two mechanisms, which one is responsible for this asymptotic behavior of delta L approaching 0. So the first mechanism, this idea of things shrinking in magnitude, we measure as the average magnitude and change in loss. The second mechanism, zero-sum learning, we measure with destructive interference. And so now that we have this derived equation that relates the mechanisms and the other contributing factors to the phenomenon, how can we actually quantify, and specifically in an interpretable way, the effect of ZSL on deceleration? I'm not really a math guy. I really like visualizations. I think they convey good intuition that can be lost when you just look at numbers. So this is what we did. the key idea is that we visualize the model training trajectories along these measures. And so here we have this 2D color plot where on the X and Y axis, you have the two mechanism measurements. So here on the Y axis, we have M for the average magnitude. And on the X axis, we have D for zero-sum learning. And then on the Z axis or the color scale, we measure the average change in loss. And so each contour line basically corresponds to a 2x reduction in the change in loss. And here we're looking at the change in loss between step T and 2T to sort of smooth the increasing noise we observe throughout training. And again, because we have this derivable function of delta L in terms of mechanisms, we can actually compute delta big L across all possible variations of M and D. And so this is how we get the contour lines. And so the next thing we do is we actually visualize the model train trajectories along these measurements. So each line here corresponds to a different model. And the top left corner here corresponds to the point of where deceleration starts. And the bottom right corner here corresponds to the point where training ends. And models are basically moving along this direction as training progresses after deceleration. And so this visualization gives us a really easy way to visually quantify the relative effects of the two mechanisms on the phenomenon. So we see that from the start of deceleration to the end of training, we cross, anything between 3 and 5 boundary lines, which corresponds to an 8 to 32-fold reduction in delta L, or the rate of loss improvement. And we can see that the y-axis contributes only a 2x reduction. So the magnitude itself is playing a relatively small role in this reduction. In contrast, the contribution from D results in, again, like an 8 to 16-fold reduction, because most of this crossing of boundary lines comes from moving along D. So I hope this kind of gives you an intuitive picture of how we can quantify the effect of the mechanisms on the phenomenon. And from this, we can, I think, pretty reliably say that zero-sum learning is quantifiably the main reason for loss deceleration, even though magnitude is also playing a role. There's an alternative visualization that I think is cleaner, but it sort of has the same underlying idea. And it's something that I think is really cool, and I want to share, even though Kate thought it was useless. But the idea is we want to understand how the different mechanisms are affecting a phenomenon throughout training. And it's very difficult to sort of intuit and understand when you're looking at not only a single point, but the evolution throughout training. And so the key insight is that if you have a multiplicative relationship, that becomes additive in log scale. So you can plot the 3 values, so delta L, M, and 1 minus D, and the shared log scale, and the plots become additive. So if you sum the plot for M and the plot for 1 minus D, you will get the plot for delta L on the left. And what this means is that we can very quickly see the relative contributions of the different variables. And we get the same conclusion we saw in the previous plots, which is that after deceleration, delta L has an 8 to 32-fold reduction. And most of that comes from the reduction in 1 minus D, again, because the effects are additive. So we can very easily see this as well. And this is something we do over and over again in the paper to quantify the effects of different variables on phenomena. I think it's a very useful tool that I hope to see more people do when studying training dynamics, because it really gives you a big picture overview of what's going on. So key takeaways for this section: we can measure zero-sum learning with destructive interference. We can derive and quantify the effect of ZSL on loss acceleration. And then with these 3 things, we show that loss acceleration is primarily the result of a transition towards ZSL training dynamics. I think more broadly, the point I want to make is that this mechanistic framing of training dynamics as per example interactions is something I haven't seen much work on, and I think is really exciting and potentially powerful and can provide new insights for understanding training dynamics. Are there any questions at this point? Yeah.
Does that still hold if you don't have infinite data?
I think it still holds, just with sort of general pictures. Not about the zero-sum learning, but the last point about the mechanistic interpretability, mechanistic framing. But I'm not sure. So we've shown that zero-sum learning is responsible for deceleration, but what is responsible for zero-sum learning? Why do, per example, changes in loss, delta L small, start interfering destructively? So one possible mechanism is per example gradient opposition. So here we have different per example gradients shown in gray, and they're roughly opposed on average. If they're opposed, then we have a given update, weight update delta theta shown here in blue. what happens is that gradients that are aligned with the update will improve. So we have gradient descent with a negative change in loss. And gradients that are opposed to the update will degrade, so a positive change in loss, because we're effectively doing gradient ascent because we're stepping in the opposite direction from the gradient, or the negative gradient in this case. And so I hope this paints an intuitive picture of how you can get zero-sum learning because of gradient opposition. But there is an alternative mechanism, which is this notion of progressive sharpening and overstepping. So here we're plotting different loss landscapes along the weight update direction for individual examples. So we're looking at 4 different examples. On the y-axis, you have the loss, and on the x-axis, you have basically the step size along the update direction. So depending on the step size, you might get loss improvements across all examples if the gradients are aligned. But if you take the larger step size, you might overstep on some examples and therefore start degrading the loss on the examples where you overstep. If your step is large enough, you can actually get full-on zero-sum learning, where the loss degradations from overstepping basically cancel out the loss improvements on other examples. So these are two potential mechanisms for loss deceleration for zero-sum learning. The next thing we want to do is see if we can rule out progressive sharpening and overstepping as a reason. So here's actual per example loss landscapes for different models at different training steps. This is early during training, so at step t is equal to 8 and step t is equal to 16. And each line is the loss landscape for a single example, and it's colored red if the loss got worse for that optimizer step, and green if the loss improved. And here in blue, we're showing the actual optimizer step that was taken at that point in training. And so we see the loss landscapes are actually very high curvature at the start of training. What happens after deceleration is that things become much more linear, and they do so consistently. So in the appendix of the paper, we had a bunch of these plots showing this across model sizes and training steps. But again, we do have high curvature at the start, but then things become linear. We also see this in the overall average loss landscape, which is the same idea of plotting loss landscape cross-section along updates, but now we're averaging across examples and showing the evolution throughout training as a 3D surface plot. So again, if you have high curvature before deceleration, and for example losses, and then things become linear, this kind of tracks with what we see here, where the overall loss landscape is high curvature before deceleration, it becomes much smoother after deceleration. In the paper, we have a bunch more more analytic analyses to further corroborate this. But the key takeaway is that overstepping can occur, especially before deceleration, but it can't explain the increase in zero-sum learning we see after deceleration. It's very unlikely that this was the mechanistic reason for zero-sum learning. So this means that gradient opposition is a much more likely candidate as an explanation. But how do we actually show that gradient opposition underlies zero-sum learning? One thing is, so in the previous section, we showed that per example loss landscapes become mostly linear. What this means is that we can model per example change in loss by using a first-order Taylor expansion, because we know the losses are mostly linear within the steps being taken. And so the first-order Taylor expansion is just the dot product of the weight update delta theta and the per example gradient nabla Li. And so again, we have the weight update in blue and the gradients in gray. And I kind of just want to give you an intuitive picture of what this looks like, because it'll be important for the next section. So when you're doing this dot product, like geometrically and intuitively, what's going on is you're projecting the gradient onto the weight update, and the change in loss corresponds to this projection, rescaled by the norm of delta theta, its non-unit norm. So we see here this first gradient is projected on the weight update, and we get a large change in loss. The next gradient, again, the same thing. We get a smaller change in loss because the gradient norm is smaller. Here, the gradient is more orthogonal to the weight update, so we get an even smaller change in loss. And now we're opposed to the gradient, so we start getting loss degradation where loss increases. And again, it's the same thing. If the gradient is more orthogonal or smaller in norm, then that modulates the size of the change in loss, the resulting change in loss. And so the reason I kind of tried to paint this intuition is because if we're going to understand the effect of gradient opposition on zero-sum learning, there's a big challenge, which is that update directions matter a lot. So here we have 2 gradients that are orthogonal in green and red. And we can see that despite the orthogonality, if the weight update is positioned the right way, you get zero-sum learning because things cancel out when you project them on the weight update. For the same gradients, if your weight update is slightly different, you get zero-sum learning. And even in extreme cases where the gradients are very opposed, so in this case the 2 gradients are almost completely opposed, you can still avoid zero-sum learning. And why this matters is because you might get zero-sum learning even if your gradients are aligned, which means that we can't really say with any certainty that gradient opposition is the reason for zero-sum learning.
Okay, it's something here. Like, why it happens? Because there are other gradients in the batch, or sorry, why this happens?
Sorry?
Sorry, why this happens? That basically, even if gradients are aligned, you can get zero-sum learning.
So if you're doing if you're doing gradient descent, then yeah, like your update will be aligned with the gradients. I don't think this actually happens in practice. This is more like an extreme example to illustrate the point that the update direction matters. I do think if you have adaptive optimizers and like degenerate batches, you could get this kind of situation where the update is misaligned. So it's this is more just like to conceptually show that the update direction matters.
Okay, thank you.
So with this, the question becomes, how do we disentangle the role of gradient opposition and update direction in zero-sum learning? So we do the same thing as before. We measure, derive, and quantify. And I'm going to give you a really high-level picture because this is pretty involved in the paper. This turned out to be a lot more complicated than what we did in the first half. But I think I can still give you the intuition pretty clearly. So here we have destructive interference in the first-order approximation of change in loss. So this measures zero-sum learning under first-order training dynamics. Then we derive this variable CG, which basically measures the effect of gradient opposition independent of update direction. And so as CG approaches 0, you can see that the destructive interference will approach 1, and so you get complete destructive interference. So basically CG approaching 0 means that destructive interference is going up, and CG approaching 0 basically means that gradient opposition is going up. Here we have two other terms, which are meant to capture the results, the destructive interference that happens from projecting the updates on the average gradient and on per example gradients. And these measure the effect of update direction independent of gradient opposition. And so we have the two plots here. Let me step back. So CG here, if we look on the plot on the left, we can see that we drop by several orders of magnitude leading up to deceleration. In contrast, the other term is much more stable, leading up to and during deceleration. So this shows us, again, in the same vein of thought of like taking a multiplicative relationship, plotting them in log space, and adding the plots together. We can see that the main contributor to the destructive interference is CG, where like things drop by multiple orders of magnitude here, and things barely move here on the right. This is roughly how we show the gradient opposition is responsible for zero-sum learning. And the key takeaways again, we can model the effect of gradient opposition by assuming first-order training dynamics. Under this assumption, again, by measuring, deriving, quantifying, show that this is the reason underlying zero-sum learning. We verify empirically the assumption of first-order dynamics is valid, so we have limit, curvature, and overstepping after deceleration. And lastly, like disentangling the effect of update directions is like decidedly non-trivial. And like looking back on the paper, I'm not even sure if we should do that because the update is very much a function of the gradients, like Alessandro started pointing at. But yeah, these are the key takeaways. How am I doing on time? 20 minutes. So we kind of have this nice building up of we explain scaling improvements with deceleration, we explain deceleration with zero-sum learning, and we explain zero-sum learning with gradient opposition. Bringing it all together, like the question we want to answer is how does scaling mitigate loss deceleration? The answer is it's complicated, and I don't think I have time to get into the details, but I want to give you a big picture that kind of summarizes what we've seen so far. So larger models have more parameters with low gradient opposition at the deceleration. We showed this in the paper. Even though their average gradient opposition is larger, the key thing is they have more parameters that have low gradient opposition. So these are like more degrees of freedom along which the model can optimize. We think this results in the mitigation of zero-sum learning, where these more degrees of freedom mean the model are able to find more shared gradient directions and therefore improve more examples simultaneously with less destructive interference. But this part is where it gets complicated. And so as a result of mitigating gradient opposition, which mitigates zero-sum learning, we get this improved post-deceleration slope, RD. And this change is basically the main reason for the improved slope, RD. So what next? I'm wrapping up with this. This is my last couple of slides where I'm trying to like look forward in terms of what I'm working on next and what I think is interesting. I think broadly speaking, the theme that I'm interested in is the idea of zero-sum learning and generalization. I think it's useful to try to actually be explicit about what generalization is. One way in which I've converged to thinking about it is the idea that generalization is shared gradients. So like intuitively, if two examples have shared gradients, if I train on one example and I improve on it, I'm also going to improve on the other example. So I'm going to generalize on it despite not seeing it during training. And so to me, like, this is a very myopic local view of generalization, but it's a very intuitive one that I think, you know, it's not novel, but I think people haven't really like addressed it systematically. And I think it's a really useful lens to look at language modeling training dynamics. And so this idea of when you have shared gradients, what the model is doing is learning shared solution, where like by improving on one example, it's also able to improve on other examples. And based on this, I have this shared gradient hypothesis, which is that after loss deceleration during zero-sum learning, the way models learn to generalize is basically by like one, forgetting and unlearning one-off solutions that don't generalize, and two, preserving and learning shared solutions that do generalize. So in other words, if we want to mitigate zero-sum learning and loss acceleration, what we want to do is we want to find shared gradients or figure out how to do that more effectively. And so in terms of things that I'm interested in, there's a lot of things we can look at to try to achieve this goal. You know, we have optimizer designs, model architectures, data sampling methods, meta learning methods, divine benevolence is always a good one. And I'm curious if people have any other thoughts once we discuss this. But yeah, this is my talk. Happy to sort of discuss now and discuss that. I have a lot of extra slides, by the way, so if people have any specific questions, feel free to ask. Way too many slides.
I think you did the session that with the data sampling methods, right? So like the type of data that you get might have a big impact.
Yeah.
So here in the work, I didn't quite understand that. What is the type of data that you're
We're doing language model pre-training. And we got the same results for different data sets. So one was with Dolma using the Olmo pipeline, and one was with NanoGPT using the Open Web Text pipeline.
you think there's like a difference if you use like synthetic data versus like data in the wild?
Yeah. So this is something that I've thought about, and I've seen like little pieces of evidence here and there. So like when people do distillation or synthetic data, I think what's going on is that the data comes from the same underlying generative process. So it becomes much easier to find these shared gradient directions, these like shared solutions, because they exist. Like we know the data was produced by a neural network that has like the same solution for all the data samples. So I think like I saw some work on like distillation and translation, where you do see this sort of evidence that distillation reduces gradient opposition during learning in the student. Then you also have all the degeneracies of like mode collapse that can happen with that. So it's sort of like a trade-off. It's something I'm really interested in and still like forming my own opinions on. I don't know, do you have any insights on this or?
No, I mean, that's what I also saw from the literature. Is like, if you can engineer like good data, you can like train faster. Like part of the training step, probably that's not easy. But like, what do you lose in change? That's the interesting question.
You lose all the 4chan trolls that, you know. I do think so. I ran a bunch of experiments earlier this year trying to do model distillation because I thought that distillation would improve loss. But what I ended up finding out after a lot of blood, sweat, and tears is that distillation by itself is actually not useful. Like the way people are doing distillation for large language model pre-training is really this idea of synthetic data. Like you're not just training on the logics of the original data.
Yeah.
You're generating new data, and this is how like Gem and other models actually improve on models when distilling. Yeah, I think it's interesting that just doing distillation with logics and original data doesn't work.
Yeah.
But something about using synthetic data will actually make your base models better than just standard pre-training.
Would curriculum learning be something that help?
So this is something I've been working on for some synthetic compositional data, and like we do know it helps. So like if the problem is sort of has large enough search space that the model can like learn overfit solutions instead of generalizable solutions, the curriculum can be the difference between like generalization and non-generalization. I think it becomes a lot harder to say reason about that for language modeling, because like language modeling is like a mixture of like a billion different data generative processes. But I think a lot of people have been showing this general idea of curriculum for like RL, even pre-training people do like length curriculum where they slowly increase the length. And you know, there's like some pretty good results out there. I'll be more confident than like when they actually become part of the standard thing that everyone does.
Yeah, I think it's really hard to reproduce as well.
And I'm curious about what's your idea of model architectures. I know we spoke about intentionally modeling.
So if you think about like why you get gradient opposition, like what happens is that output gradients and your input activations. So for a linear layer, the gradient is just the outer product of the output gradients and the input activations. And so if like one of those is correlated and the other one is anti-correlated, you're going to get gradient opposition. If they're both correlated, you're going to get, gradient alignment. If they're like orthogonal, you're going to get gradient orthogonality. It doesn't matter. So like really the root of the problem is this idea that you get, anti-correlated inputs or correlated inputs and anti-correlated output gradients and or correlated gradients. But, like intuitively it makes sense because if the model has learned like the same features, so the same input activations for two examples, but they have different ground truth labels, then of course you're going to want to like learn different gradients where like one is learning a different feature than the other, so you can separate those out and better predict them in the future. And so just from this like very fundamental idea of like input activations versus output gradients, I think there's a lot of like things you can look at in terms of the architecture to try to minimize that, especially because like self-attention is just a massive pooling operation. So if you think about the difference in input features for like token T versus token T plus one, if your T is at like 1,000, like most of those input activations are identical and your like change is like tiny relative to the overlap. So it makes sense that attention is very prone to this sort of gradient opposition. I do want to show you guys something really quickly, which was surprising. So people were asking about, which tokens are more, let me see if I can find it. All right, here it is. Which tokens are interfering with each other? And so what I looked at is this idea of like in-sequence zero-sum learning. So how much do tokens in the sequence interfere with each other versus cross-sequence? So if I average in the sequence and then compare sequences, what does it look like? What was really surprising is it looks basically the same. So these are different. There are like differences. It's not a bug in the code. But like if your data is large, like if you're looking at a large enough amount of data, zero-sum learning. So here on the y-axis we have destructive interference of change in loss after one step. In the top row we have in sequence for the training batch. In the top row we have the results for the training batch. So we take one optimizer step and we look at the change in loss for the data used in that step. In the bottom row we have the same thing for another without a validation batch. And then top column is first column is in sequence and second column is cross sequence, and basically they're indistinguishable. So given enough data, like this statistical phenomenon seems to be like, doesn't care if you're looking in sequence or cross sequence, which to me was surprising because I think most work on gradient opposition like looks at continual learning and looks past learning where we have this very like nice discrete ideas of tasks. So, like I was posting on Twitter a while ago, and this guy posted like, oh, this is just continual learning. Like we know that gradient opposition is bad. Like this is different because it's not that you're looking at like different tasks. Like within a single sequence or like within a single example, you get the same phenomenon. So to me, this sort of points at something more fundamental about like, transformers and attention and this idea that input activations are very correlated by default. And so you almost, by definition, end up with high gradient opposition. And we actually measure gradient opposition in the paper. I didn't get into it because the measure is a bit difficult to communicate, but it starts off really high. So it starts off around 0.9 and then goes up to like 1. But the fact that it starts at like almost complete gradient opposition is really surprising. Yeah, all that to say that I think the architecture is a big reason for why we get gradient opposition. I don't think it's a bad thing though. I think we want gradient opposition because this is how you actually find shared solutions.
Okay. Compression.
Yeah.
Does the sequence length have any effect?
Yes. I don't know if I have the results in these slides. No, I have like 120. It's not that much.
So the comments that I thought that some of the slides were useless, I didn't say they're useless.
Sorry. It's being self-deprecating. I'm sorry. Okay, this is an earlier attempt at this talk that I think I have the slides on. So in the paper, we do have an ablation where we look at sequence length and batch size. If I can just find it, right here. Here we go. So here we trained two models. Everything is the same, but we vary the batch size of the sequence length. So here we're looking at fixed batch size, and we're varying sequence length. So the total number of tokens is the same. So like, this one will have like 4,000 sequences, and this one will have 2,000 sequences in the batch. And so What I think I want to communicate here is that we know that longer sequences are easier to predict because you have more context to
Yeah.
condition on. So what's surprising in this plot is that the difference in performance really arises only after deceleration.
Yeah.
So the reason longer sequences are easier to predict is because of in-context learning. I think most people will agree that this is a big part of it, maybe not the whole explanation. And so again, the fact that longer sequence training starts improving after deceleration is again like an interesting observation that there might be a correlation with generalization. So this is the only experiments I have on sequence length. I don't know if this answers your question. If you want to follow
Do
up
you feel
on it.
that there's less opposing gradient as the sequence increases? There's less place for ambiguity because you have more context to resolve those ambiguity.
I think once the model starts learning shared solutions, so like once you go in the second phase, yes. Yeah, but I don't think it has less gradient opposition. I think it has more chances to like resolve gradient opposition. But because the sequence is longer, like I'm not sure if that balances out or not.
Okay, yeah.
Do you know if like hyperparameters might be some issue, like
I mean-
training rate or eventually?
Definitely. So some experiments I ran last summer that it was during an internship, so I have to rerun them because I don't have them anymore. If you make your learning rate low enough or your warm-up schedule long enough, so basically if in the start of training, your learning rate is moving up too slowly, what happens is you get deceleration around the same point, but at a higher loss. So you get the same shape, but like shifted upwards. And so like clearly like learning rate matters in terms of this phenomenon. But I don't know why.
And batch size, it's to enter smaller batch.
Not sure. I think all of like these things have like very different, like complicated phenomena. Like in principle, like bigger batch size is good because you have less noise. But like something about this seems to suggest that the noise is good because you need the noise to actually converge to a better solution. If you have a big enough, if you have too large of a batch size, you might just end up overfitting the batch more. I'm not sure. I think a lot of these things end up having like affecting many different things that interact together, and it's difficult to reason about. But one thing I do think is relevant here is that it makes sense to look at these separately before and after deceleration, because we know things are qualitatively different. I think maybe people will try things and see it doesn't work before deceleration and they give up, whereas maybe it would make sense to try them only after deceleration.
You show on the slide where like the dependent optimizer, right? That dependent back, like getting to the deceleration faster. And you try like in that hybrid approach where you use the muon and then after that you switch to LMW.
No, I haven't tried that yet.
Because you were mentioning how to, what are the mechanisms that are responsible for that, and so we can design a better optimizer.
Yeah, it's on the long list of things I want to try. I do think like for the optimizer, there's something interesting that I'm particularly interested in. I don't know if people are familiar with Reptile and like the meta learning sort of algorithms, like MATLAB and stuff like that.
Yes.
Yeah. Like basically what they do is like they'll take multiple gradient steps, compute the difference of the weight updates after the gradient steps, and like use that as a pseudo gradient from the original point. And the idea is that pseudo gradient has like a second order term that increases the alignment between the batch gradients of the multiple steps you took before.
So they can roll back and apply the pseudo gradient at that.
Yeah. But the main thing is the pseudo gradient is like captures a second order term that increases gradient alignment between batches. And if you look at like momentum and atom or actually momentum, it's actually doing the opposite, where like it's the same sort of idea where like you're looking at gradients from previous steps and applying them to the current step.
Right.
But because of this difference in direction where like Reptile looks at future gradients and goes back, and momentum looks at past gradients and goes forward, you actually get like a sign reversal where like Reptile will increase alignment, but momentum will actually decrease alignment if you assume that like, that paper is correct. So I think this is like an interesting design like axis to look at. How can you modify momentum to, have more incentivization of gradient alignments? I don't know if that makes sense.
You said if there's more chance that the update will be in some different direction if there's some lag because of the optimizer. Like Adam or something, we will consider previous gradient. So instead of being fully aligned, might, how can I say? It might mess up like the overall gradient oppositions.
Yeah. Like one thing that's interesting, like at Dynamics, the optimizer do after deceleration. Like the thing they do is they add like a third momentum term that has like a much longer memory. So like normally beta would be like 0.9. They add like a 0.999 beta. And so like the clearly seems to this idea of like having a longer memory after deceleration is useful. I don't know if this means that like you're somehow finding more shared gradient directions, or you're just like not forgetting things as quickly. Anyways, I think like reasoning about this from the idea of zero-sum learning gradient opposition is potentially promising, but also might be futile, like a lot of other things in deep learning. But we'll see.
I think it's really surprising to, like you said at the beginning, that graded position is the explanation of this.
For sure.
Yes. All right. I guess now is a good time to stop, unless there's other questions.
I'm happy to chat offline after if people want.
Yeah. Do you want to stay for lunch or?
Sure.
Yeah.
Thanks.
All right.
Actually surprised I finished 20 minutes early. Sure.
100 slides.